Special relativity. General derivation of Einstein's energy-mass equivalence relationship E equals mc². In relativity, the mass of a particle increases when its speed increases. The momentum of mass moving with velocity v is given by the formula. The force acting on a mass m is the rate of momentum change. Substituting mv in the previous equation and deriving with respect to time t. According to the definition of velocity. But the derivation of position vector with respect to arc length is the tangential unit vector, and the derivation of arc length with respect to time is the speed v, hence. Substituting this result in force formula. According to Frenet-Serret formulas, where r is the radius of curvature at point S on the curve, and n is the normal vector at the same point. Substituting that in the previous force formula. We arrive at the general force formula in classical and relative physics, with the difference that in relative physics, the moving mass changes according to the formula m0 times square root of 1 minus v square over c square. From which, we see that the first tangential force is, and the second tangential force is, and the normal force is. When the particle is displaced along the vector ds, the differential work will be. The dot product of vectors is 0 when the angle between the two vectors is 0 degrees. But substituting that in the previous equation, we arrive at the general differential work formula in classical and relative physics. Work in classical physics. If the mass of the object does not change, dm equals 0, then the differential work will be. Assuming that the particle moves from point 1 where its speed is v1 to point 2 where its speed is v2, the work the force field does on this particle can be computed from the integral. In classical physics, the kinetic energy of a mass moving with speed v is given by the formula. Hence the work of the force field can be written as work in relative physics. In relative physics, the mass m changes with the speed of the particle and is given by the formula. Substituting that in the general differential work formula. Differentiating the term. Finding common denominator for the fractions. Adding the fractions. Since. Then. Substituting in the differential work formula. Assuming that the particle moves from point 1 where its speed is v1 to point 2 where its speed is v2, the work the force field does on this particle can be computed from the integral. The rest mass and the speed of light are constants. They can be taken out of the integral. In relativity, the kinetic energy of a mass moving with speed v is given by the formula, where m is the relativistic mass. Hence, the work of the force field can be written as the work of a force F acting on particle whose rest mass m0 can also be written as where m1 is the mass of the particle when its speed is v1. m2 is the mass of the particle when its speed is v2.